discussing the Hamiltonian N1. And that one is in some sense even nicer than the Lagrangian one. But and you can develop the theory just starting from scratch. But because we already discussed the Lagrangian mechanics, I will basically start from Lagrangian and then proceed to Hamiltonian by the Legendre transformation, as people typically do. So the first task to discuss is the Hamilton's canonical equations, which were formulated in 1834 when Hamilton was 29. And so basically the advantage is that the Euler-Lagrange equations, if you have n degrees of freedom, you have n equations which are second order. So now we will trade them for 2n equations which are first order. So you are gaining something, you are losing something else. So the first step, if you start with Lagrangian, is to define the canonical momentum. And so if you have the Lagrangian, you just define Bj to be dl over the qj dot. And so this is the definition of your momentum. So now notice that I'm writing some indices down and some indices up. So the q's have typically index up, whereas p's have typically index down. The reason is that, strictly speaking, they live in different spaces. So whereas so these guys basically live are components of the forms. So they live in the cotangent space, and these guys are something different. So these are just coordinates. Okay, so they live in different spaces. That's why I will try to put the indices down for J and for P, and for Q, the index up. Okay, so now once you have the canonical momentum, you can introduce the concept of the phase space. So the Lagrangian mechanics typically takes place in the configuration space. Which is the space of the positions. And it sort of describes a photo of the system. So where the particle is at a given time. And so the coordinates on this space are just these qj's. And there is n of them. So if you have n degrees of freedom, the dimension of this space is n. Okay, and so, for example, you have a motion on an asteroid. This is my asteroid. So at each given time, so this is my configuration space, and then I sweep a trajectory like that on my asteroid, and at any given time, I simply have q of t, and then at later time, I will have another q of t, and so on. So you sweep a trajectory in this configuration space, but because you have only q's, this doesn't really describe the full physical state of the system, because I can be here at a given time, but I can have different velocities, and then I can go this way or that way or whatever. So just if you take the picture, it doesn't describe the full physical state. On the other hand, the phase space does describe everything, and so describes physical states. Physical states. And so now we have 2n coordinates, and there are the positions, but as well as the momenta. So the dimension is now 2n. And so again, if you consider this motion on an asteroid, so this is your trajectory, but at that given q of t, you don't only have the information about where you are on the asteroid, but you also have an information what your momentum is. And so the momentum, as I said, lives in, it's a tangent thing, so it lives in a tangent space to this asteroid. And the whole thing So configuration space, let's call it C. But now in the phase space, I have the information about Q of t, but also P of t. So you have to imagine that every point of this asteroid, you have to imagine that there's this extra space where the momentum lives. And so this is called cotangent space. So this is the star of C. Okay, so you have, and the dimension is twice as much, and it has informations about positions and informations about velocities. Of course, people are much more used to thinking about these type of pictures. Yeah, I used to thinking about, I have information about Q, I have information about P, and this is my trajectory in the phase space, right? So the same thing. Okay. So now for those who have taken some differential geometry, this is just a manifold, and this is the cotangent space over that manifold. And you will learn about this in the relativity course. So don't worry, this picture will become clear once you take the relativity course. Yes?
Are you saying just P lives in T star of C, or both live in T star of C?
So the cotangent space has both. So it has these coordinates Q and P. So it's like a fiber bundle over the manifold. Yeah. All right. So phase space, much nicer quantity because it carries the information about what the actual physical state is. So now, because we are starting with the Lagrangian description and then you're proceeding to the Hamiltonian one, then the Hamiltonian is simply defined as Legendre transformation of the Lagrangian and there is this everybody known formula. So now you have the Hamiltonian, which is a function of Q, P, and T, possibly, and it's given by P, I, Qi dot minus the Lagrangian. But of course, the Lagrangian is a function of, okay, so the Lagrangian is a function of Q, Q dot, and T. But you have to evaluate the left-hand side in terms of Q and P instead of Q dot. So what you have to do in the end is that you have to plug in that Q dot is a function of Q and P and T. Okay, so this is how you really get the Hamiltonian. So in other words, I have to be able to invert the relation for P, right? I have to, so that gives me P in terms of whatever the things are Q dot. But in order to write down the Hamiltonian, I have to write Q dot in terms of P. And this is not always possible. And if it's not always possible, then actually you have problems. And typically this is solved by constraints. You have some constraints and stuff like that. So the fact that you cannot invert this relation for Q dot can be origin of big problems. But it happens in gauge theories and it happens in other things. So we have to deal with this problem. So anyway, so we are in mechanics. So let's assume that we can always invert it, and then you have just function H is a function of Q and P. Right. So now, once we have that, are there any questions? So now you really want to rewrite n Euler-Lagrange equations to 2n Hamilton equations. So the system of n Euler-Lagrange equations is equivalent to a system of 2n first-order equations, Hamilton's equations, and so these are Bj dot, and so there's one minus sign, and I never know which one it is, but you should know it's minus dh over dqj, and then qj dot is dh over d pj. That's So these are the Hamilton's equations, and the statement is that they are completely equivalent. In case you can actually do this Legendre transformation, they are equivalent to the Lagrangian formulation. Okay. So one way to show this theorem, to prove this theorem, is to really take this definition, and let's say I want to prove this equation. So I know what H is. It's given by this Legendre transformation. So I just differentiate it with respect to P, massage it, and hopefully find that it's equal to Q dot by using the Euler-Lagrange equation. So you can do that if you want. I think it's instructive to rederive it again from the action principle. So the proof will be through the action principle. So we still want that the action, the variation of the action, is equal to 0. So we require that this is true. So now we are back to normal delta without tildes. So that's the delta which has the fixed endpoints and which leaves the time untouched. And so now what this is just a delta. So now the action was L dt. Okay, so now I can write L as PQ dot minus H. So it's PQ dot minus H dt. So this is your L, and so you have the same action, but now you're just writing in terms of different variables. So now what is different here is that you treat P's and Q's as independent variables. So you'll be varying P's independently to Q's. Okay, so let's do this. So it's an integral from 1 to 2. Okay, so now I have Q dot delta P, and then I have P delta Q dot, and then I have to vary H, and H depends on Q and P. Okay, so there's minus dH over dQ delta Q minus dH dP delta P, and the whole thing is dt. Hopefully it's still correct. So really to stress, I am treating P and Q as independent, and that's the powerful thing. So now in the end, we want to massage it into something times delta P and something else times delta Q, but because they are independent, whatever stands in front of delta P and whatever stands in front of delta Q have to be 0 separately. So again, what you want to do is that you want to shift. So you have delta Q dot, and you want to shift that dot onto your P, right? So you integrate by parts as you did before, and you pick up a boundary term. So the boundary term is simply P delta Q from 1 to 2. And then you have an integral from 1 to 2. And let me collect the terms which have delta P, let's say first. So the first term does have delta P, so it's Q dot. And then the last term has delta P, so it's minus dH over dP, delta P. And then the terms which have delta Q. So now if I integrate by parts, I pick up a minus sign. So it's plus. I pick up a minus sign, and there's also minus sign, plus P dot. And then plus dH over dQ delta Q dt. And so because these are independent, this guy has to be 0, and that guy has to be 0 independently. And hopefully that has the right signs to get your Hamilton's equation. Questions? Everybody seen this? Hopefully.
What if the Hamiltonian depends on time explicitly?
So it doesn't matter in this variation. So remember, this variation delta leaves the time completely untouched. So
if the Hamiltonian depends on the time explicitly,
then the energy is not conserved and whatever. But
what should be the modification?
no, but this still goes through. So even if h is a function of t, when you impose this variation principle, you don't vary t, right? You fix t and you vary just the q and p, right? So this will not change. This will still be true. So now, very good to your question. So notice that whatever dh over dt is, so now I actually do the variation with respect to t. So it's dh over dq, q dot, plus dh over dp, p dot, plus dh over dt if I have explicit time dependence. All right. So now what you do is that you plug in for q dot from your Hamilton's equations. So this is dh over dp. And for p dot is minus dh over dq. Minus dh over dq. So now if you look at this term here, it's dh over dq, dh over dp, minus dh over dp, dh over dq, and they are exactly the same, so they cancel. So the first two terms actually cancel, and this is simply given by dh over dt. So, to your question, if h is not function of t, so if h is not explicit function of t, then dh over dt is 0. So what does it mean? That the Hamiltonian is conserved. So it's a conserved quantity. Yeah, and so we invoked the equations of motion. So of course this is true on shell. Okay.
Just a question. Maybe a very trivial one, but why do we vary the action with respect to fixed time delta? Why are we not varying it with respect to the tilde one?
Oh, because yeah, just simply so remember in the picture yesterday, you are just considering variations where you fix time, and so this was your delta q. So you do the variation. So you're trying. So you know that your motion was here at one time and it's here at another time, but in principle it can sweep all the trajectories in between, whatever the trajectories you have. So now the variation principle is picking up such a trajectory which leaves this action variation 0, right? And so how you do the variation is that you say, well, I fix t and then I consider all these types of trajectories here. And so they represent this delta q. And yeah. And so action is stationary only for one trajectory here, which is precisely picked up by this delta s equal to 0. And so this is what's going on.
So this is because of the fixed endpoints. And if we have this tilde on delta, it means that we are translating it as space or time.
You could, yeah. So this delta tilde in general has not fixed endpoints, and it's
Okay,
and it also changes time. Yeah. All right. So that's the Hamiltonian description. So by the way, I just wanted to show you this picture. You've probably seen it. So Legendre transformation is not important only for mechanics, but it's important for other fields. And one of them is thermodynamics. So you do Legendre transformations in thermodynamics all the time. So intermezzo. Do you know what intermezzo means? So what does it mean?
A short break in the main development of things.
And typically people call it when you listen to the opera or whatever, or movie. So, okay, very good, thanks. So, Legendre transformation. Transform in thermodynamics. So, of course, now people just look up the Wikipedia if they need to know what Legendre transformation for thermodynamics is, right? But there is this very nice magic square. So there's a magic square. And so you know that the variables in thermodynamics are, you draw a square. Now, the thermodynamics in variables are volume, temperature, pressure, and entropy. Of course, you can extend these variables by adding electric fields and whatever, but these are the basic variables in thermodynamics. And so then you have these basic thermodynamic potentials. So I recall this picture when you'll be doing statistical physics. So you have the internal energy, you have the free energy, you have the Gibbs free energy, and you have the enthalpy. Okay, so big mess. So you have 4 different potentials, depending on which Legendre transform you do. Okay, so now this is still not the end of the story. So in order to this is still a square. So to make it a magic square, you need to assign some signs. So you have plus here, and minus here, and minus here. Now it's real magic. And so just following the rule from electromagnetism, there's an arrow always going from plus to minus. Here we go. So that's the magic square. Okay, so now the statement is this magic square contains all you need to know about thermodynamics. So first of all, what it tells you, so first question is, you typically never know, okay, I have free energy. What are the variables? If you want to write the differential of the free energy, what are the corresponding variables? What is free energy function of, right? Which precisely? So now it's very simple. It's always so the corresponding thermodynamic potential is a function of the nearby quantities. So the statement is free energy is a function of volume and temperature. Gibbs free energy is a function of temperature and pressure and so on. So for example, the free energy function of volume and temperature. Okay, so now if you want to write down the differential, and that's very useful, right? So if you want to really find out equilibrium situation, all these thermodynamic potentials are typically minimized or whatever. So you need to know how to write down the corresponding differential. And that's the basis of 95% of calculations in thermodynamics. So it's a function of volume and temperature. So there must be dV plus something else, dt. Okay, so now what is that something else? So it's always the conjugate quantity, which is just directly opposite to whatever you see. So P and V are conjugate quantities, and S and T are conjugate quantities. So now you are having PV, but there's this magic sign minus. So it's minus PdV, and then it's minus, better to write always minus first, minus S dt. Okay, so this is the potential. This is the differential which you are looking for on your Wikipedia page or whatever. So is this clear? So let's say I want to do dg. So dg. So g is a function of temperature and pressure. So now there's a minus sign for this one. So we minus sdt, and then plus v dp. Okay, and so on. So it's okay. So that's first thing which you really read. It's 95% of calculations in thermodynamics. So the remaining 5% of calculations are Maxwell relations, which I'll notice in a minute. But I call it, well, how the Legendre transform behaves. Well, so all these thermodynamic potentials are connected by the Legendre transform. Okay, so going from one to another is just changing. So if you have u, which is a function of s and v, and you want f, which is a function of v and t, somehow miraculously you have to change s to t, right? That's precisely done by Legendre transformation. So let's say I want from u, which is function of v and s, to free energy, which is function of v and t. So basically I have to change s to t, and that's done by Legendre transform. And again, you follow the magic sign. So you see, I'm changing S to T, but T has minus sign here. Okay, so the free energy is U minus TS because there is this minus sign standing in front of T. Okay, so that's how you do the Legendre transformation. Of course, similar to our P, right? So our P is TL over dQ dot. So now our T will be du over ds. Okay, so that's the Legendre transform. Okay, so finally I said the remaining 5%, or maybe let's put it 90%, 10% are Maxwell relations. And so these are interesting relations between various partial derivatives of various quantities. So for example, you want to relate dV over ds at constant p to something else. And the way how it works is that, so I want to do dV over ds at constant p. So I swipe this triangle here. And the statement is equal to the triangle opposite. Okay, so now I draw the opposite triangle. So the statement is it will be dt over dp at constant s. All right. And then you are interested in the sign, and the sign is, okay, so you draw this triangle, and whatever at the bottom is, there is the sign plus, the sign plus, so there's two pluses here. So now if I wanted a different one, so for example, I wanted dV over dt at constant p, it would be ds over dp at constant t, but now one of them has plus, and the other one has minus, so there'll be minus sign, one minus sign on the side. Okay, so these are triangles. This equals to that, and then the sign you read here. So there's the sign here, and there's the sign here. Okay, and so they form the remaining 10% of the calculations in thermodynamics. So I'm just giving you this, in case you don't have access to Wikipedia. So of course you can show these relations by simply looking at the differentials and saying, so for example here, what you know is that S is dg over dt, and V is dg over dp, right? But now we can swap the derivatives or whatever and equate the things, and because the partial derivatives commute, you have to get some expressions in between the two, and this is how you derive these Maxwell relations. But anyway, so this is really nice. So anyway, so use it if you want. Don't use it if you don't want. Questions? Okay, at the end of intermezzo, we can continue. So part B, very interesting structure is that of Poisson brackets. And let me start with the definition. So let f and g be two phase-space functions. Phase-space functions. Then their canonical bracket, their canonical Poisson bracket is a new phase-space function. Is a new phase-space function defined by f and g. So it's a binary operation. I take two functions and produce a new one. and it's given by df over dqi, dg over dpi. So you are summing over I. Sorry, I should have said that a long time ago. Minus dg over dqi, df dpi. So here, everywhere, a long time ago, I'm using the Einstein summation convention. And so people try to estimate how various scientists were really economically viable. And they realized that for Einstein, the best thing is really introducing the Einstein summation convention, because he saved lots of paper by not writing these sums and everything. So that saved lots of money, actually. So now we are summing over all possible i's here. So if you have 3 directions, you're summing over 3 directions. All right. So anybody hasn't seen this? Everybody's seen it, right? Okay, that's perfect. So now some properties. Let me just summarize this. So by using this definition here, you can easily check all these properties. So one of them is fundamental brackets. And it's simply that Qi and Pj is delta ij. That's the canonical delta. It's equal to 1 if I equals to j, or 0 otherwise. And then Q's, whatever, Qi, Qj are always 0. And so are Pi, Pj. And so from the definition, it's almost obvious that I differentiate once with respect to Q and once with respect to P. So for example, if I have 2 Q's, you must get 0 immediately. So now this is a trivial consequence of the definition, but it's very fundamental. And of course, this serves as basis for quantization. So when you quantize quantum mechanics, you just, or even in field theory, you always find Q and P, and then you promote these to operators or something, and then you just replace the Poisson brackets with commutators, and you add some randomly add some h bars and whatever, and that's how you quantize things. So by the way, of course, that's the wrong direction you are going, right? So you are starting with classical theory, and you are going to the quantum one, which can't be done. Quantum theory is more fundamental, and so the right direction is that you start with the quantum theory, and then you take the classical limit, and the classical physics should emerge, right? So there is no way how you can derive quantum mechanics from the classical one. It's only heuristic argument, if I try this, I get this quantum theory, and then of course in the end you are interested, is this consistent with experiment or not, right? So, but the right direction is, if I know what is the right quantum theory, I can take the classical limit and get classical physics out of that. Okay, so that's the property 1. That's not the right one. Okay, 1. Property 2 is the antisymmetry. It's symmetry. Obvious by this minus sign here. So if you have f and g, it's minus g and f. You have linearity. So if you have alpha, which is a number, times alpha plus beta times g on h, it's alpha times f and h plus beta times g and h. Then you have the Leibniz rule. Well, it's a derivative, you better have it. So if you have f, g, and h, it's I differentiate, okay. I differentiate the first one, fh, and leave g untouched, and then I differentiate the second one. So I have g and h, and leave the first one untouched. Okay, and I am deliberately writing this, that whatever was on the right stays on the right, and whatever was on the left stays on the left. And the reason is that this can be true also for matrices and whatever. And so, yeah, this can be generalized beyond the functions. So finally, the nice property is the Jacobi identity, which is a really mysterious one, but very powerful one. So what you do is that you take Poisson bracket of fg with h. So now you have 3 Poisson brackets, well, 2 Poisson brackets like that. And then you cyclically permutate these things. So you have fgh, so the next one will be hfg, and the last one will be ghf. So h, f, and g, and then g, h, and f. And if you do it, you miraculously find that the combination is equal to 0. Okay, so these are the properties. So now they are all consequence of this definition of the Poisson bracket, but in some sense you can take them as definition of the Poisson bracket as well. If I take properties 1 to 5, they will define what you mean by Poisson bracket. And because you studied now the algebras, this means that Poisson brackets actually form the algebra. Okay. So now it's very interesting to see what happens if you relax some of the properties 1 to 5. And so Feynman was playing with this in 50s, and so what he basically relaxed is one of the fundamental brackets. So I think what he kept Q and P, which is dot ij, and he kept Q and Q equal to 0. But then he said maybe P and P is not equal to 0. And so if you do it, you actually derive electromagnetism. And you will do it in tutorial next week. All right, so you may be looking forward to what happens when some of these fundamental brackets are not as you are used to. Okay. Question? So now, using these Poisson brackets, of course, you have the time evolution captured by these Hamilton's equations, but you can also write down the time evolution in terms of the Poisson brackets, and the expression is very nice. So if you want df over dt for any function f, so you have f dot, then this is given by, okay, let me just write down the result, fh plus df over dt. So that's the result. Of course, the proof is just one line. I just have to write it as df over dq, q dot, plus df over dp, p dot. I use the Hamilton's equations, and I use the definition of the Poisson bracket, and this is what comes out. Okay, so that's how you write time evolution. It's really, really beautiful. So if you have no explicit time dependence, then time evolution is simply given by Poisson bracket of whatever you want to evolve, and the second sort is given by the Hamiltonian. Okay, so specifically, if you want the integral of motion, so we know that the integral of motion is something which di over dt is equal to 0. This will never happen if I depends on time explicitly. Okay, so if I want di over dt equal to 0, by definition from Lagrangian mechanics from yesterday, that means that h has to be equal to 0, and if you want, people take this as a definition of integral of motion in the Hamiltonian mechanics. So now there's another interesting property, is that these integrals of motion form some kind of algebra. with respect to these Poisson brackets. So given two integrals of motion, I1 and I2, and taking their Poisson bracket, you can show that this guy is again an integral of motion. I'm not going to spoil your fun by proving this. You will do it in tutorial tomorrow. So this seems is very, very powerful, right? So let's say my system has two integrals of motion. Then I may think, well, I'll generate another one by taking the Poisson bracket of these two. I get a third one. Okay, but then now I have a new one. So I can do I3 and I1, and I get a fourth one. And I get I4 and I3, and I get a fifth one, and so on. So this would be very, very powerful. But unfortunately, this is not typically the case. And typically, this terminates very, very quickly. So you actually find that most of the integrals do commute, Poisson commute, so you get 0 here. And so 0 is an integral of motion, but it's not a very helpful one. Okay, so typically terminates quickly. And yeah. Questions, comments? Yeah.
So are all of these functions that we're applying the Poisson brackets to, should we think of them as being functions of Q, P, and T explicitly?
Yes. Yes. Exactly.
Then why can we say that the total derivative...
Sorry, why?
Why can we then say that the total derivative of I being 0 requires this? Couldn't there be implicit... Sorry.
Well, okay. So no. So I went through this very quickly. I don't know any integral of motion which could explicitly depend on time. Simply doesn't happen, because if you have explicit time dependence, it just doesn't. It's not conserved in time, right? So I'm saying integral of motion basically shouldn't be explicitly time dependent, but also this is the requirement, right? So then I have this. Yeah.
Does the Hamiltonian have to be a scalar?
Oh, you asked yesterday, right? So the answer is typically is, but yeah, you can formulate theories where it's not, but we don't have any.
But it's a different geometrical object than the Lagrangian, right? Because it takes an element in the manifold, like coordinate, and it also takes a vector in the tangent space.
It's a different object. I agree. It lives in a different space and stuff like that. But I'm saying so. There are theories where you can make it something more complicated than a scalar, but they don't find any application.
But for example, in quantum mechanics,
right.
The Hamiltonian usually can be written in a eigenvalue basis and have the form of a matrix or a tensor. So, and the Lagrangian is never written like that. You put it in a different way when you quantize.
That's an interesting question. So, of course, in quantum mechanics, I promote H to be an operator which lives now in functional space and whatever, an infinite dimensional something. Yeah. Here I'm talking about classical mechanics. Other questions? But basically, what you should be asking is, do I need to describe quantum mechanical system by, let's say, 3 Hamiltonians, which are the operators? I would have H1 hat and H2 hat and H3 hat, and that never happens. Of course, H hat is a complicated object, but it's still only one of them.
I have a question. How do you know if the I3 you got is redundant or not? Of course, if it's 0, it's redundant. But like, could be a linear combination of I1 and I2.
Yeah, sure. Yeah, I can use linearity.
Something more complicated, but not new in any way. How do you check that?
Yeah, you have to check that whatever the integral of motion you are getting is sort of functionally independent to previous integrals. You have to check that. So an example where you get something new is, let's say, the angular momentum, right? So if I have two conserved quantities, let's say my angular momentum is conserved in x direction and in y direction. So then you plug it in, so I have Lx and Ly conserved. You plug it there, and you get Lz. Okay, and that also has to be conserved. So what it's telling you is that if your angular momentum is conserved in two directions, it must actually be completely conserved. And so that's a new non-trivial integral of motion. But yeah, maybe you get something else, and you get a combination of L1 and Lx and Ly. Then this is not a new integral of motion, because of course I can add integrals of motion, and they are not like producing new functional independent ones.
If there is an inner product defined, we can check it.
That's right. Yeah, there's ways how to check whether it's functional independent. Yeah, thanks. Part C. So now, this is quite powerful notion as well. Canonical transformations. And basically, canonical transformations are behind the fact that Hamiltonian mechanics is very, very powerful. And so Hamiltonian mechanics, similar to Lagrangian mechanics, has certain freedom. So remember, in the Lagrangian mechanics, we could add to Lagrangian a total derivative of a function which is a function of q, and the equations of motion didn't change. So now we actually have much bigger freedom in Hamiltonian mechanics, and let's see what this freedom is. And so we can do canonical transformations on our descriptions on our Q and P, define a new Q and P, and so provided that this transformation is nice, you get the same equations of motion, and you can use this to actually simplify solving these equations. So definition, I'll give you this rather confusing definition of canonical transformation. So a canonical transformation is such a transformation of your coordinates so that you define a new qi, qj, which is a function of the original ones, qi, pit. So these are the original. And then similarly, you define new pj, my new canonical coordinates, qi, pi, and t, and so q and p are new. So these are the new ones. Such that one can find new Hamiltonian let's call it h prime now as a function of qj and pj and t. So now it's a function of new capital variables q and p. One can find such new Hamiltonian so preserving the form of Hamilton's equations. So what it means is that now, with respect to these new q and p, we will have exactly the same form. We will have pj dot is equal to minus dh prime dqj, and qj qj dot is dh over dj. Okay, so this is very confusing definition, isn't it? So this could be any transformation. I just take my old q and p's and define arbitrary function of these old q and p's, be new q and another p. So in general, you will not be able to find a new Hamiltonian so that the Hamilton's equations take the same form. Okay, the form will change. It is exactly the same thing as if you start with the Newton's first law, F equal to ma, which is valid in an inertial frame, right? So now you transform to a non-inertial frame, to a rotating frame or whatever. So suddenly your force law will become much more complicated. You will pick up so this F is the real force, right? So this is the real force. But if you go to a rotating frame, you suddenly create these Coriolis forces and whatever, right? So you create lots of crap, and your force law will be much more complicated. So similarly, if I do arbitrary transformation here, my canonical equations will suddenly be much more complicated. So now I'm specifying only two such transformations which leave this canonical form of the equations same. Okay. So in some sense, here I'm restricting to connecting frames, be inertial frames, right? I can go from one inertial frame to another inertial frame, and F equal to ma will remain the same. So similarly, I am choosing such coordinate transformations which preserve this. Yes?
Sorry, this might be a bit technical question, but is the H prime Hamiltonian the new one? Just the old one with Q and P's plugged into it?
No.
Okay. No.
No.
Okay.
So this is really, you will see, it's almost that. In most of the cases, it is that, but not necessarily. So sorry, this is new H prime, this is the new H prime. I was missing prime. It's a very good question. So now I have this stupid example which doesn't really prove anything, but I'll show it to you anyway. So not every transformation is canonical. This is not a proof what I will show to you, but it's just a heuristic argument that it actually might not be. So be very careful, this is not a proof, even for that particular case. So let me just consider the motion of a free particle. So in my old coordinates, the Hamiltonian is given just p squared over 2m. And then I somehow decide, somebody tells me a stupid idea, that my new q should be square root of my old q, and that my new p is just small p. So the question is this transformation canonical? The answer is it is not, and you can rigorously prove that, but let me just show the heuristics why it's not. So let me use the idea that maybe H prime actually is the same thing. So I can guess that H prime will be P prime over 2m. So let's assume that H and H prime are the same things, while small p is capital P, so this is the original. So this is my guess. Okay, so then you can calculate what dH prime over dP is. dH prime over dP is, well, it's P, capital P over M. Which is small p over M. But small p over M is just dH original over dP. But I know that dH original over dP satisfies the canonical equations. So this must be equal to q dot. So here I'm using the canonical equations valid in canonical equation here. But Q is Q square. Small q is capital Q square. So Q dot is 2 times Q dot. Okay. But if this were a canonical transformation, this would have to be equal to Q dot, capital Q dot. But it's not. So this sort of heuristically shows you that this probably is not a canonical transformation. This is not a rigorous proof. I haven't shown you that really this is the right H prime. Yeah. So then the question is how to find these canonical transformations, right? So if not every transformation is canonical, and it's only the canonical one which actually leaves the form of the equations, the nice one, then how to find these? And the answer is that all such canonical transformations are actually generated from some function. So there is a generating function. So given any function, I can generate a new canonical transformation. So canonical transformations are generated by generating functions. What else it would be? If I want to generate something, it must be a generating function. Canonical functions. So now, what is a generating function? Well, it's a function. Let's call it f. And it's always a function of an old coordinate and a new coordinate. So now, the old one, what I mean is small q and p. So you pick up one out of these. You pick either q or p. And the new one is the capital ones. So now if I'm in one dimension, so I have only one q and p, one q and one p, then I have 4 possibilities. I can choose QQ, I can choose QP, PQ, or PP. So 4 possibilities. Of course, if I'm in higher dimensions, I have many more possibilities. And so what is actually miraculous about this, it doesn't really matter which possibility you choose for generic systems. That's a caveat. So typically the systems which you deal with are very, very simple and are degenerate. And if they are degenerate, only one of these generating functions will work. And the other ones will not produce anything useful. So, but let's assume we have sufficiently complicated system. And if you have sufficiently complicated system, it doesn't matter which combination I choose. So let me choose small q and capital Q. There will be one generating function. And the other ones, actually, for generic system, will be given by Lejeune transformation. Okay. So let's pick f, which is a function of small q, and in principle, it can be also a function of time. So this is for sufficiently complicated systems, sufficiently complicated H, this is without loss of generality. because if you pick the other ones, you would just get Legendre transform of whatever we are getting here. All right, so we are picking up this function here, and you will use the freedom in the Lagrangian description of your thing. So remember, we could do L to L plus D of function d lambda of Q over dt. So the statement is, if I consider S, which is given by my original L, which however now I write in terms of the Hamiltonian, so it will be P and then Q dot minus H. So this is my old Lagrangian. Then I can add or subtract a total derivative of a function, and that's what I will do. I'll subtract here. I don't know why, but doesn't matter. So this is precisely the freedom in Lagrangian description. So I can add a total derivative of a function, and this will be true. Okay, so now what is this? So this thing here is just an integral pq dot minus h, and then I have minus df over dq, q dot. And so remember, f is a function of small q of my original coordinate, capital Q and t. Okay, so it's not a function of p. So now, but capital Q depends on time. So now I differentiate with respect to capital Q, and then potentially with respect to time as well. All right, so now let's collect the terms. So this is equal to an integral. So let's put whatever. I have Q dot. So then I have P here, and I have minus df over dq. And then let's collect. Then I have also this term minus df over dq, q dot. This term here. And finally, everything else is minus h plus df over dt. Just grouping the terms together. I haven't done anything, just terms. All right, so this is so far what we have. We just exploited the freedom in Lagrangian mechanics. So now we want this to give us the same form of equations of motion. But in terms of capital Q and capital P. This will certainly be true if this can be written as PQ dot minus H prime P, Q, and T dt. So if I start this action like this, PQ dot minus H prime, this is just my new Lagrangian in terms of capital Q and P. If I do the variational principle, I'll just get the standard canonical equations, but now in terms of P, Q, and H prime, right? So this is what you require. It's what you require. Okay, so now let's do this, and let's do it like really, definitely not like mathematicians. So let's compare term by term, right? So first of all, do we see here any small q dot? We don't see any small q dot here, right? So that means whatever stands in front of q dot here has to be equal to 0. Right? So I want to kill the term with small q dot because I don't have it here. And so that's why whatever stands there has to be equal to 0. Then whatever stands in capital Q dot has to be P. So this thing has to be capital P. And then I have minus h prime, so whatever is left must be h prime. So we are getting these beautiful relations that small p is df over dq. That's one requirement. Capital P is minus df over dq. And h prime is h plus df over dt. All right, so now we can claim the victory, right? So for any function f, I know how to find canonical transformation. The canonical transformation is given, so fixing f, I just find new p like that. I have to, this has to be satisfied, and then the new Hamiltonian is given by this. So in particular, if f does not explicitly depend on time, then I find that h prime is equal to h, which is the answer to your question. So only if f is not a function of time explicit, then h prime is h. Of course, I have to plug the right variables. The h is function of small q and p. This one is function of capital Q and p. Right? So only in this case I have h prime equal to h. But if f explicitly depends on time, then there's this addition of this thing here. Questions, comments? All right. So this is how you generate these canonical transformations. So basically, fixing f, I can find a generating function. To every f, I will find the corresponding canonical transformation. So now let's assume a different thing. So assume we have we are given a transformation. A transformation. So then the question is how to find its canonical. Is it canonical? So one way to show that it is canonical is to find this generating function f, which is quite painful, but can be done typically, at least for simple systems. But it is a much easier way, and that's basically checking the integrability conditions for these relations. And so, but even easier is to actually check the Poisson brackets. So the statement is, if you have, statement is that Poisson brackets are invariant. And the canonical transformations. So in other words, if I have f and g, and I calculate it in terms of small q and p, then this must be the same as if I calculate it in terms of big q and p. Okay, so why does it help? Well, I can choose specific function of f and g. I can, for example, choose small q and p. I know that this is 1. But now I have this, given complicated transformation. And so if I calculate it in terms of capital Q and P, it gives me some conditions. And so checking these conditions tells you, is my transformation canonical or not? So now, why is this true? Yeah?
Are Lorentz transformations being seen as canonical transformations?
Lorentz transformations. So what is it we are doing? Let me think about this. So there you're talking about relativistic systems, first of all. So you are not changing Q and P, you are changing only Q. Now I have complete blank, so let me postpone that question. Initial systems, probably they are. Okay, let me postpone that. I'll try. All right, so how to see this thing here? So let me use Landau's logic. So if you open Landau's book, of course you can show this by explicit calculation, but it's pain. But if you think about, so what this thing here is. So let's for the moment, so Landau's logic. Landau's logic, which is actually correct this time, is that you think about G is some function as a Hamiltonian. Okay, so G, well, why any I have any function G, but why not to think about it as something which generates my time translations? Okay, so in other words, let me plot it here. To every function in the phase space, you can actually assign the corresponding time flow. Hamiltonian is just special function. It's just, one special choice of the function, but any function will do the same thing. So if you think about G and H, then this generates time flow with respect to some time t corresponding to G function. And then you can think about F and G as simply, if you look at, so I have no explicit time dependence, but this is this equation lurking at us here. This one, that one, you can see it. It's lurking at us there. So I have no explicit time dependence. So then the time differentiation is just given by the Poisson bracket, right? So what this really is df over dtg. So it's just time evolution of function f with respect to the time provided by function g. Okay, you can also write it as there is a vector field generated by G acting on function f. So what I mean by this is I have P and Q. So now I have some function G, and this generates time evolution. So there's my TG here, and so at every point, there's a tangent vector, which you will call xg. And so this vector is called Hamiltonian vector flow. And then the corresponding curve is an integral curve of this vector flow. But anyway, so I'm just thinking about this as a Hamiltonian. It generates some kind of time translation in my P and Q. Okay. Very good. So now what this really is telling you is how much the function f changes as you move from this place in the phase space to, let's say, that place in the phase space, right? So now if I change whatever I mean by P and Q, these points remain untouched, right? So it doesn't matter how I parameterize P and how I parameterize Q, just this df over dtg will remain the same. It's an invariant quantity. It's a geometrical quantity. It's just the distance between the 2 points. It has nothing to do with coordinates, right? So this is certainly coordinate independent. So doesn't matter if I choose capital Q or capital P, or if I choose small q and p. And the change of the function as I move along this thing here has to be the same. The function will have the same value here, well, and the same value here, no matter if I change this guy. Let's say I rotate a thing or whatever, I have Q and P, well, this will still remain the same. And that's why this thing actually has to be true. Yes?
I don't understand what TG is.
Okay. The statement is, I can assign a vector field to any function. So you fix a function in the phase space, and then there is a unique prescription how to get a vector field. That vector field, so you have a vector field xg, and it's given by the Poisson bracket something g. So what is this thing? If I just use the canonical definition of the Poisson bracket, so there is nothing here in this first law. So it'll be d of nothing over dq and dg over dp minus dg over dq, d of nothing over dp. Okay, so this is what it is. So now if you look at that, I can swap these two terms, this one and that one. So this is a differential operator. If I swap these two, this is a dg over dp times d over dq minus dg over dq, d over dp, right? So this is a differential operator. It's a derivative with respect to some direction, right? So I'm picking up how much, so this tells you how much you go in q direction and how much you go in p direction. Right? It's a directional derivative. So this is a directional derivative. So it tells me a direction in the phase space. I move that much in the q direction, that much in the p direction. But directional derivatives are nothing else than vectors. So this is also a vector. Tells me how much I have to go here and how much I have to go there. So this is my corresponding vector. Okay, so now I have in my phase space, P and Q, I have a vector. It goes like this, goes like that, goes like that, goes like that. Okay, so everywhere in the phase space, I have this vector defined. So now it's a theorem that I can actually find an integral curve of this, meaning a curve which is always, so that the vector is always tangent to this curve. This is an integral curve. Okay, so you have this integral curve, and so you have a special trajectory in the phase space. Okay, so the Poisson bracket gives you a trajectory in the phase space. So fixing g, I get trajectory here, but of course this will be true also for other things. So I get all trajectories penetrating my phase space. Okay, so now what you can do is that you can parameterize this trajectory by some time. Okay, so meaning if I'm here, let's say I choose, so this is a trajectory generated by this function g. So I choose tg equal to 0, let's say, and then later on I choose tg equal to 1 and tg equal to 2 and so on. So as I move along the trajectory, I'm just changing the corresponding parameter, which parameterizes my trajectory, the time. So in other words, the Poisson bracket, for any function g, I can write this Poisson bracket here. It gives me the vector field. That vector field gives me the curve in the phase space. And the parameter which parameterizes this curve gives me the time. So this is precisely this time here. So now so I can write this thing as d over dtg. Does it make sense? So now we have covered, I don't know, 3 hours of differential geometry in this one slide. So but the statement is like Hamiltonian. So if there were Hamiltonian here, right? So you would just say this is just normal df over dt, where t is the time associated with your Hamiltonian. right? The statement is Hamiltonian. So what it means is that Hamiltonian produces this vector field, produces these curves in the phase space, and tells me how to evolve in time in the phase space, right? So that's what Hamiltonian gives you. So now the statement is Hamiltonian is not any special. It's just a function in the phase space. Hamiltonian is a function of Q and P. It's not special at all. So if I take a different function, G, it's also Hamiltonian, but it gives me a different time evolution. It gives me a different curve. And so this is the statement here. Now we ran out of time. Are there any more questions here? Yes?
Just to make sure I understood, here you suppose implicitly that f has no explicit dependence on the parameter or the time, right? Okay.
I think so. Yeah.
Thus, there would be like a...
Yeah.
I have another.
Yes?
Like P and Q, like the phase space, it doesn't have to be flat. So this directional derivative, would it be least derivative?
Oh, well, what I was telling you is associating the differential operator, directional derivative is a vector, is a completely general statement. So the vectors actually live in flat space. So even if you have curved manifold where the space is curved, then actually people typically consider, if you want vector space is nice and flat, it's linear, right? You can add vectors and stuff like that. So vector space is never curved, unless you are Lee-Smolin and you invent something where it actually can be curved. So vectors are linear objects, and so that's why they are, the vector space is not curved. That's the standard. But I'm talking about something else than I wanted to talk. So, yeah?
Sorry, but J is a function in phase space, in the complete phase space.
Yeah?
And XG is the one that it's in the tangent space.
That's right. Exactly. So, yeah, that's right. All right, so let me stop here and continue tomorrow.